What's up, everyone? We're back for another Polymath Salon online, this time with Yo-Yo and Lucy, and they're going to be presenting on scent computing. Now, I'm sure many of you have heard me talk for on and on and on forever about, olfaction and my whole olfactory language thing. And the reason I'm so excited today is I think there could be a lot of synergy and intersection between some of our ideas. And we've actually talked a little bit at length about this in the past, but this is also going to be kind of new to me. So I'm like super excited to hear this straight from the source. So before Yo-Yo and Lucy start their presentation, how about a quick bio from both of you, and then we'll go to our guests.
Yeah, sure. My name is Yo-Yo. I'm fairly interdisciplinary. So in the past, I read some science fiction. I explored quantum computing, and then in my bedroom, I hacked with biosignals as well as built with like swarm of robots. And nowadays, I'm looking just a bit about sun computing and cognitive science. And also, I'm a CS student at Minerva University.
I'm Lucy. I do mostly electronics and hardware stuff. I'm really interested in edge machine learning and distributed systems, and I'm doing a lot with environmental sensing and LoRa mesh right now. And yeah, that's kind of my background.
Yeah, howdy. My name is Daniel Van Sant. I'm a computational neuroscience PhD candidate at Florida Atlantic University. I am interested in making humans smarter by making AI smarter. So I have a dissertation on automating neuroscience research I'm working on, and I also have a product I'm working on that allows people to do deep dives on sort of interdisciplinary topics.
I'm Michael Ostroff. I'm a PhD physics student. I mainly specialize in general relativity and complex systems.
Hey, I'm Dean. I'm kind of like a home tinkerer. I've worked with like Sensorion, like CO2 and PM2 sensors, but just for fun. So I'm just interested to see if is it possible to train an ML model to figure out if my dog pooped or not, just for fun.
Hi, my name is Neil. I am a master's student at the University of Waterloo, having a background in mechatronics, and I'm currently tinkering around with social robots.
Okay, so I will talk a little bit about sun computing from the cognitive science high-level perspective. Recently, there are AI wearables that can store your day in terms of text descriptions or voice recordings. So raises the question if scent is also a memory device. And startups have also grown neurons to taste Coca-Cola. So how do these biological noses compare against human ones? In the case of human noses, we have first some flowers, maybe releasing odorant molecules that travel through the nasal cavity onto the epithelial layer of human inside the nasal cavity. And there, the odor molecule binds to some receptors that are resting on top of neurons. Then in bundles, these neurons go to the glomeruli, which is where they first spatially come together. It's similar to clustering things. And here is an example of that glomeruli. Afterwards, they will be sent to the pyriform part of olfactory cortex and finally embedded with memories and emotions and decisions in the orbital frontal cortex. So in the case of lemon smell, the molecule of limonene binds to receptors like OR1A1, OR2J3. There are 400 types of receptor genes that are encoded each on a neuron. So it is also similar to a 400-dimensional vector space that are clustered later together. And here's an example of bionodes developed by UMD Research and the startup Aeromics, which are used to taste liquids, which is really incredible because that means the liquid will directly touch the neuron and be perishable. So let's have a nose showdown between the biological grown ones and the human ones. Firstly, in human noses, it takes 100 to 200 milliseconds from odor detection to perception, and at around 300 milliseconds, some decisions begin to be made. In bionoses, it takes longer, 250 to 500 milliseconds. You have to also factor in that it takes 15 to 21 days for rat stem cells or human stem cells to mature into neurons that can be used. And each culture can last 7 to 21 days. So in the human nose, it exists on a 10 centimeter square epithelial layer containing 10 to 20 million olfactory neurons. And as I mentioned previously, there are 400 receptor types. And in the BioNose case, the overall platform is around credit card size, and the most essential area, the sensor area, is 4 to 25 millimeters squared. In that area, it is a microelectrode array composing of 4,096 pixels on the chip. So we can look at some practical metrics. Like in the human nose, it costs nothing to record some sense, and the energy is using 1 to 2% of what the brain produces, which is around 0.5 watts, and precision is 10 to the 12 cent mixtures can be distinguished. And if you have a strong, particularly unpleasant mixture, the sensing precision is parts per trillion. In the BioNose example, it takes first 10K development for the wetware, and then per sniffing, you need to grow the neuron culture from stem cells. So it costs around 100 to 2,000, 200. The energy cost by the sensor area is 3.58 milliwatts, which is really efficient. That also ties into the sparsity and the grid cells working. And overall, considering the GPUs and the computer setups related, the cost of energy goes up higher to 5 to 20 watts overall, which is higher than human nose. And the precision is slightly less accurate than humans at 0.01 parts per trillion. And as previously mentioned, these cultures have a lifespan, and after 10 days, the viability drops by 50%, whereas in humans, you usually adapt to the smell within seconds, and the firing rate drops by 50% after merely seconds. What good are these noses? We have, first of all, down-to-earth applications, like sensing various organic or inorganic gases. Then you can detect diseases. An old lady supposedly can smell Parkinson's disease and dementia or Alzheimer's, or just like diabetes releases acetone and liver failure is associated with ammonia. They can be smelled. And finally, we can integrate it with a smart home module, which is really portable. In the creative realm, there are applications with storytelling, so authors can use sense to enhance their passages, as well as video game designs. Cultures, for example, there's Japanese temple incense recipes that can take decades to master, and Amazonian rainforest healers can use 40 or more medicinal plants. So if these knowledge go extinct, it will be better to have them stored as a digital database of things. Another thing I like to ideate is the transmutation between senses. For example, text to scent. The first thing we created is where we cluster 3 essential oils, lavender, orange, and lemongrass, with a $20 sensor. And here are some visualizations of, I think it is humidity and gas resistance. Well, of course, with some artifacts. And because, remember, there are roughly 400 receptor types in the olfactory system. Similarly, it's not an exact mapping, but there is a 384-dimensional space that the vectors are stored in. So if 2 vectors are close together in this hyperspace, they are more similar. By this principle, we can use natural language to search through them. The second transmutation is between sense and visuals, particularly fluids. So in this case, we had a box in the demo where it's surrounded by different scent bottles where the sensor will be in the middle, and we began by interpolating a coordinate grid around the sensor. And then we turn that into a scalar field. Using diffusion and advection, we can simulate fluids in real time from the sensor data. So now we have some speculative applications about communication between human-animal, animal-animal, as well as human-alien. So at the center of it is pheromones, which are chemical signals between members of the same species. And there are similar pheromones which contain information about the organism itself, such as when a mother uses the pheromones to find her newborn that has the genetic odor printing, as well as the releaser pheromones that trigger immediate behavioral responses, often linked to sexual attraction. Some examples where humans interacted with animals through pheromones are replicating the moth pheromones and the sexual pheromones to distract them for the sake of pest control, and also detecting pheromones associated with aggression in elephants in this period called moose to warn the animal guardians ahead of time for their safety. And dogs can also smell human scents through breath and sweat. So if the human owner is particularly stressed, dogs can sense it, and studies have shown they exhibit more ambiguous responses to food and rewards, and linking to a more pessimistic outlook on life in general. This suggests that good communication is not just the transmission of information from the sender to receiver, but is also a closed loop mechanism. You can also consider the channel capacity as well as the complexity of the signal being communicated. In animal-animal interfacing, there have been studies comparing the spatial memory for fire ants and honeybees and finding that they have been similar. In terms of alien witnesses, there are usually consistent smells of sulfur, ozone, and ammonia reported. Sulfur is the rotten egg smell, and one famous incident is the 1967 Falcon Lake observation in Manitoba province in Canada. There was a little boy that observed the alien spacecraft that is stereotypically shaped like a tart and has this circular ring of glowing panels. So when he touched the craft, his gloves melted away as well as his clothes, and there was physical damage done to his skin from the glowing lighting he has to be treated at the hospital for several weeks after, accompanied by some vomiting and diarrhea behaviors. So another scent is ozone, associated with lightning and electricity. And finally, ammonia is just the pungent smell we usually associate with pools. Interestingly, the observers of aliens don't have a higher mental illness level compared to the baseline population. The one hypothesis is these are what aliens use to metabolize. So scientist Clara Souza Silva from MIT has been studying phosphine for the last 10 years, and she observes that although the molecule is really toxic toward oxygen-using organisms, it's really beneficial toward anaerobic organisms, and they take high energy to be created. So that means it's only found in live chemical reactions with few false positives linking to other kinds of formations of phosphine and making it a good biosignature to be detected. The other hypothesis is they can be communication mechanisms from the aliens if they're directly speaking to us, attacking our subconscious, skipping the thalamus as previously mentioned. And they would use sulfur, as some authors describe as deathly unpleasant, associated with the underworld, etc. But so far, if aliens are communicating with us through sense, there has been no decipherable message. And to think about deciphering olfactory languages from aliens in general, how would you even go about it? Without a positive negative feedback, you can use some associations perhaps, or some statistical observations, but you have to make sure that it's testable and plausible. So to conclude part one of the presentation, scent technology also includes bionoses, and it's more than just human nose and the traditional hardware e-nose. They can transmute into other modalities like between text and sound and fluids. We can easily interact through them with language models nowadays, which we still have to explore. And there are some speculative cool use cases with human-animal and human-alien communication. Now I will pass it on to Lucy, who will talk more about the sensor as well as the PCB.
So as Yo-Yo was saying, scent is like a highly contextual sense. It's very underrated. Humans make poor use of it a lot of the time. So many animals rely very heavily on smells. I have snakes and keep snakes. And one interesting thing about snakes is you can infer how excited they are pretty easily by how often they flick their tongue, because that's one of the main ways that they navigate the world, and that's how they get a lot of the context about their environment. So one of the reasons smell is so interesting is because it is fuzzy. So there are an array of sensors that each have cross sensitivities to compounds that don't really correspond to any given scent. Like with taste, there are like very clear dimensions that kind of are intuitive, right? Like we can map taste to these 5 basic kinds of taste. Odor is way more complicated. It is a very combinatorial, fuzzy kind of processing. So identification of scents is highly complex, and it is kind of intrinsically multimodal. Like we'll get into this more later, but the training process is weird because you really are like, you have to be labeling the things as you're doing training, and that like you're using the fact that an array of sensors respond slightly differently to an array of compounds that aren't really directly the thing you're sensing, and you're kind of looking at the combination of all of them. And so let's talk about how we do that. This is a Mach sensor. This is the basic structure. So there is a heated, and let me make sure I have that. Okay, we're good. There is a heated little membrane here and a metal oxide layer. And basically, you can think of it like this. There is a resistance across the metal oxide, and it is temperature dependent, and it is dependent on the composition of the atmosphere around the oxide itself. And the resistance changes depending on so it's sensitive to a number of different things. Most sensors are not really just sensitive to one particular thing. So if we look at these charts over here, we can kind of see what I mean. So here, like, we're looking at, let's say, like a spike of ethanol in the air. So this is typically how gas concentration is going to change. You're not really going to ever see gas like, or I guess I should just say this is kind of the curve. If you just open a bottle of ethanol, this will kind of be what you expect to see across the room in terms of the concentration over time. And the response by the sensor will like change depending on the specific temperature of the membrane, which we'll use later. And you can see that like maybe if you expose it to several different things, if there's several different compounds in the air, the heat applied can change the actual like response differently depending on the specific mixture of compounds. So maybe like at some temperature, there's some response. Well, we'll get more into this later, but so this is kind of the basic theory of Mach sensors. And so the fact that it's like combinatorial and we're looking at the cross sensitivity to all kinds of different compounds and applying these heater profiles that give us different responses to different mixtures makes this a very easy machine learning problem. What we really want is an edge machine learning model that can, first, we want to find a profile that, well, okay, let me back up for a second. An individual Mach sensor, to get it to identify a specific gas, right? There will be this change in the composition of the atmosphere, and there will be a change in the resistance across that we're going to see. When we start to put several of these in an array that each have slightly different sensitivities to a different compound, then we can start to like tune it, if that makes sense. Does this make sense intuitively? Like the fact that we like, so if we have like a specific concentration of ethanol and a specific concentration of say methane, and as we change the heater profile, it gets more sensitive to methane and stays the same in ethanol, then we can start to differentiate. And we can kind of scale this up by using an array of different actual gates with slightly different cost sensitivities with different heater profiles. And that will give us like selectivity to specific compounds. And this is kind of what we're going to build into a more refined olfaction system. So really the two problems are, first, we need a sensor with a tunable response to very low concentrations of some array of compounds. It's fine if it's sensitive to multiple things in a way that's hard to differentiate, as long as it is tunable and as long as the response changes differently to different things as we tune it. And the second problem is that we need to then take that and figure out how to actually identify and label specific scents. And that is a solved problem, sort of. There are a number of systems to do exactly this. So here is the BME 688. And what it is basically just, can you see this? It's 8 metal oxide sensors with controllable heaters. And we can apply a profile to the heaters to give us sensitivity to, or like that's how we're going to end up tuning it. And then we can mix the output in different ways to try to identify specific gases or to maximize the selectivity for specific gases or scents. So Bosch has released the sensor, and along with it, this firmware called BSEC, which is just, it supports an array of common microcontrollers and has all of, the I2C commands to actually talk to the sensor, and then it has AI Studio for the actual training process. But this is limited in a number of important ways. So these really are made for, like, the trick that we're using here that we're going to generalize to a more broad electronic nose is really made to give a low cost platform that is like tunable to detect one specific thing for a given commercial or industrial application, which we'll talk more about in a second. But some of the applications that exist are like, say you're, a chemical processor and there's one specific pollutant that you want to monitor for. And you just want like Bosch doesn't want to release a million of each sensor that's tuned like to only be sensitive to one thing. They want to actually be able to leverage the fact that these sensors are intrinsically like cross sensitive to lots of different things and use that combinatorial input in the same way that your nose just kind of like does on its own to actually use that for greater selectivity and tunability instead of being a con. Does this make sense? Like, if you were only trying to detect one specific compound in an application like this, you could do all the research to find that there's one specific, metal oxide layer that is just like only sensitive to this one specific mix and really changes with when that's applied. It doesn't really change with anything else. You'd have to do hundreds of iterations of different material processes to find that, yada yada, versus they're using 8 here, and it gives crazy cross sensitivity to all kinds of things. So like one of the existing commercial applications is if you saw at CES this year that like the baby cradle that like detects diaper state, like that's a use case that they advertise in their data sheet. So to the dog, detection or whatever, that's just a listed application. And so I have basically, this is my board. Can we, yeah. This is a very simple implementation of that Bosch MOX array with an ESP32 microcontroller to let it connect over Wi-Fi or Bluetooth. I'm a big fan of Bluetooth Low Energy Mesh, which would provide a pretty cool platform for some interesting things we can talk about later. It has an SD card slot on the back. I haven't populated that right now because I haven't really needed to. And then just the USB-C interface and all. Very minimum implementation. So here's the board. So I'm using a toolchain called Adafile to design this board. I won't get too into it. If you would like to play with this, just know the board itself is basically a Python package that you can install. This is like the whole thing. There's a Git repo where you could just order it assembled somewhere in here in the actions. If you go to actions, don't worry about the fact this is a building, I'm sorry. But in the build artifacts in here, there's the PCBA files. So, and then here's the actual KiCad project. This is a simple implementation. Let's talk about how the actual trading process works. So this is just from the BME AI Studio kind of documentation here. There is the initial training round where like, so the first recording, you kind of got to get a baseline of the sensor. Each one has a little bit of variability in the actual response. So again, the actual output is going to look something like this for each individual sensor, where there's these kind of waves of gas resistance as things kind of move around in the air. And you'll like sweep through the different changes and look at the resistance over time, or sweep through the heater profiles and all these things. And it's just kind of figuring itself out. And then there's the first training where you label some condition, you show it something, and you just have it smell it for a while. And the air is moving around and the levels are changing over time and all this stuff. Just because of the way airflow works, that's kind of why you get these like, wavy patterns, just as it transitions around. But so we have these, and this example, this is from a paper called an odor labeling convolutional encoder decoder for odor sensing and machine olfaction. All of the systems are basically the same. They use an array of the different MOX sensor inputs as the sampled several times over time. That's this layer here. So in this paper, they're using, I forget what it's called, like the Pen 3 electronic nose. Very simple implementation, or very similar to the BME 688, just with 10 instead of 8 sensors, and it's slightly older actually. That's the first layer. I don't exactly know, I'm not really a machine learning person, so if you want to get into the weeds of this, you should read their paper. But the output of all of this is that when you label the conditions, and this is related, I think, to like the training and the reinforcement process are the same, where you're like labeling things as you're teaching it, and it's adjusting the weights of like the heater profile and signal mixing of the different sensors outputs over time to basically have the output like matched with the label arriving at where you want it to, like as you're exposing it to the condition that you're trying to get it to select for, which they go more into here. But like that kind of makes sense practically with how you do it with this. Like you're basically just like moving between conditions that you're putting the board in front of to train it. But so then you end up getting a vector space that the different labels are kind of encoded in, and then like depending on how well, let me show you also when I say the heater profiles. When
I have a quick
board,
question
yeah,
because
go for it.
because like these boards are all slightly different, and the temperatures may be slightly different as well. I guess it's not really possible to have like a pre-trained data set that can be like used by other people kind of a thing. Like I would have to like train it for a pear and then train it for, an orange and kind of a thing. Is that correct?
So it depends on the particular sensor. So in this one, I think that like the actual like gas resistance to different concentration is within some percentage, but because of like how low the concentrations involved here are, it's like parts per billion, like is the sensing threshold for these kinds of things. I think it's hard to get it really dialed in and generalizable to a specific platform. However, I do think that there is a way to like a lot, like how should I say, the higher dimensional space that you get from the training, I think that you can like align it without doing the full training process somehow. I don't exactly know how this works, but I saw this alluded to, so that you don't have to like completely recalibrate from scratch every time. But I know that there is work on this that if you message me after, I can point you to.
It's good to know. I guess so. I'm from what I'm hearing is like if you take the like 300 dimensional space and you compress it into like 12, and maybe that 12 can be used. Is that kind of
Well,
like
so you're only like you're starting with the gas resistance measurement of the 10 sensors sampled over time, and then that's this first input layer here. And so because of how extremely sensitive these are, and like it's just like it's impossible to like how should I say, the exact resistance versus concentration response is going to be different sensor to sensor, but it's going to be different in a relatively consistent way, such that if you align one specific vector in the higher dimensional space by figuring out like how this should be arranged to do that, it should align the broader matrix, if that makes sense. Because like if one sensor is actually like twice as sensitive as another one to a specific like volatile sulfur compound, then you should just be able to like accounting for that and for like just one particular fruit or whatever should kind of loosely align everything else, if that makes sense. But so there are actually ways to get around that also though, which I will talk about now. Like the problem of right now, like this works really, really well if you individually like train it in the environment more or less, or you only like train it for one specific thing. Because like the problem is if you set up the heater profile and mixing so that it's really only selective for one very specific thing, it's pretty reliable and like resilient. But when you start trying to do like multiple types of things, that's where it starts to get really sensitive like this without additional kind of grounding. For just like, how should I say, there isn't really a good baseline for it. Like, which is one of the things that we need to address. So this, I'll talk about it here. Like the areas to investigate to make it more kind of repeatable and like enable like a more general sensing platform would be more sensors and newer sensors. So like first we should just do additional, so like 64 total actual MOX sensors if we have the ATME688, and see how many different things we can detect with that. And then we might also want to try additional sensors with other sensitivities. Like for example, there are like this one here is called the FPA30 or something, and it like can detect specific common volatile sulfur compounds, or like in like to a very precisely calibrated level, and like things that are like common background sense, which will like that's kind of the point of this also. But then also it can do laser particle sizing in one of the units that it's attached to, which might be useful to kind of supplement the like pure combinatorial, MOX gate input. And then there's other like additional degrees of freedom that you can add, like, or I should say like additional ways to try to tune sensors. So like there are some metal oxide sensors that use the like heated gate, and then also they use like the pulsed ultrasonic transducer below it, and that somehow can like tune the response to like specific subsets of compounds, so that you can like differentiate more easily like what the specific response is coming from. Like, and that's kind of like I feel like I'm kind of dancing around this, but like the reason that you have a hard time grounding things is because you're looking at the combinational like input of a bunch of different highly sensitive like receptors. So that's like powerful and for the same reason not very grounded. And so like giving it like a sense of the baseline with sensors like this that are really, really sensitive to a given very specific compound that will like affect the readings broadly, like for all of the different sensors, might be a good way to make the system more resilient and generalizable also. So like these are, as I mentioned earlier, there are some metal oxide gates that have like very known like specific responses to like all of the common gases that you'll see or whatever, and they're like made just to detect one specific thing. Supplementing with those and the gate, or like the array of just the general purpose MOX sensors might be another fun way to do this. And so olfaction can like, back to this starts to get way more expensive. The fact that you can already like, these are already just using the BME688 to do the like differentiating different fruits, and then they also later in the paper detect rot and stuff. If you want to detect a given thing, it's already possible to do as long as you train in the environment or have a way to train in the environment, with like a single one of these, like, $15, it's 8 MOX gates sensors. To scale up using the same principle starts to get a lot more expensive and specialized, but it's already so crazy that you can do this pretty much with whatever with a $15 sensor. But so it can be implemented cheaply on low power, widely available hardware. The tools to detect specific gases with cheap arrays like this can be extended more widely. And we need to be teaching computers how to smell. Last thing I'll point to, this is one existing application of the BME688 to detect like specific environmental states in a big mesh network. I do a lot of stuff with LoRa mesh. Here's a very simple mesh network board. This can transmit several kilometers, dozens of kilometers in good conditions on very low power. This is 700 milliwatts of solar panel. That's probably enough to run several of these full time and then be sending data back to a base station. This is a system that's being used already to detect fires with this exact sensor. And I think it would be really cool to do all kinds of environmental sensing with this type of thing, and not just detect fires, but also it would be cool to visualize all kinds of sense moving through the environment. You could do all kinds of interesting zoological and environmental research. That's all I have. And if anyone has questions.
That was awesome.
Very interesting. So
Yeah,
I came in late, but I'm curious of the detection mechanism. So it's like this metal oxide layer, and chemicals come in, and then I saw the diagram in one of the slides. It seemed like oxide components would leave the chemical and get bound to the metal layer, and then it would detect that. Or
yeah, so each individual sensor, I feel like I kind of hand waved this a few times. It's simple but also esoteric. It's just that the resistance changes when you expose it to a given gas, a lot. Maybe a mega ohm or so, with a change in 1 part per million concentration. Any individual metal oxide gate is not sensitive to one specific compound. It will have a variable response to, say, a given sulfur compound, a given volatile organic compound like ethanol, something like that. And so the gas is going to be a complex mixture of all of these different things that it's responding to. And we expect different gases and they're to evaporate more or less quickly over time. We expect different gases to be present in higher or lower concentrations. And then also if we have different actual sensing units that are present that have different specific sensitivities to different specific compounds, we can compare the response between them. And we can be okay, this one is more sensitive to this specific sulfur compound than this one, and it went way crazy. Maybe it's that specific sulfur compound. And we can kind of compare between all of the different sensors and start to get a much clearer picture where the sum, it's greater than the sum of its parts or whatever. And that's kind of that's just how the structure of scent works, where it is a highly combinatorial set of different cross sensitivities. So none of the stuff is really mapped to. Oh, sorry.
You have an array of sensors, and they're all tuned to different temperatures, I guess, and so they're recording different. Or do you have one sensor and you vary its temperature? And
yeah.
see
So the
response curve goes.
Thing is, the temperature of the gate changes the sensitivities to different things, and not in a linear way, I guess. So
it's different response curves for different chemicals, and that's how you suss it out. So it's you have to tune a radio, tuning a radio. You have to sweep the band. You have to change the temperature on the thing, and then see how the responses are, and then do some combinatorial machine learning type of pull the signals out. And then
it's exactly like tuning a radio. But also the other complicating factor is that if you do tune the heater profiles and mix the signals in such a way that you're maximizing this the selectivity for one specific compound, often you end up not being able to sense other things well. So there's kind of a this is kind of where the training process is interesting. And this is where you get a lot of benefit from tons of different sensors.
Could you take one sensor and then vary its temperature throughout the whole range, and then record the data, and then suss out, say, okay, it hit this sweet spot, so this is here, that's here, kind of a thing. Maybe
I'm not exactly sure why this is the case. I think it's the case that metal oxide sensors don't respond well to that kind of sudden change in temperature, but they do respond well to the pulsed ultrasonic as another way to modulate them. So that's kind of where I'm interested in playing with these newer, weirder ones that instead of being made for like selecting for a specific compound, like in an industrial application, like they're much more tunable for this purpose. Like, so the pulse ultrasonics an area to look into that more. If you want to try to like sweep through really rapidly to just like, and that like the way you can think about
not rapidly, just as fast as it would naturally want to do it. You know, whatever the sensor wants. But that's my question is that the idea?
Yes.
What range of chemicals are available to be sensed by this apparatus?
I mean, truly, like it works for any, like try it and it'll probably work. Like,
I mean, for instance, does the chemical have to have like oxide groups hanging off of it, or can it be, you know, what types of molecules are available?
I think it's natively sensing volatile organic and volatile sulfuric compounds, but they're just like those tend to be associated with whatever other scent in specific levels and mixtures to a like degree of reliability that is effectively whatever. In the same way that like, you know, like the actual chemical sensitivities don't have to map at all to like intuitive dimensions of scent. In the same way that taste does. So just the sensitivity to the common range of VSCs and VOCs is enough for almost anything.
As far as applications, like I can think of like a dozen. Could it be sensitive to animal or human pheromones? Can you read people in some sort of way?
So I feel like the hard thing there would be that you have to be able to like it really benefits from the environment, or like, sorry, the event that you're trying to detect being very distinct. So like, I wonder if it's easy to have like, I mean, the problem I think would be triggering, you know, the pheromones reliably, I guess, and like have like actually setting up the training conditions. But
I think they have.
It is sensitive enough that it should chemically be able to do that. And this is kind of to like what I think, like to Yo-Yo's point earlier about it being like a kind of innately kind of more embodied sensory mode, and the way that you know, is probably related to it being neglected in computing. But,
I mean, a related
Yeah, like
question.
they have been often used to sense, sorry to cut people off. They have been used to sense a lot of like the insect pheromones in research context for pest control. I think it's just the sensitivity is difficult because I remember sensors have like parts per billion sensitivity.
The related question is like when they're selling these diaper sensors, are they training each module when they ship these, or is it somehow like the module can have like these really set parameters that are extremely reproducible?
I think, and this is kind of to my, like what I was trying to say earlier, I guess, is if you pre-train it and you're trying to maximize the selectivity for one specific condition, you can make it pretty resilient to the, you know, the specific operating environment. And I think that that's what they do. Like they're like, the complicated thing will be like having it reliably detect this one event trained in an array of different, you know, like environmental conditions. Which
So
is
it,
kind of
like in their paper, when they're demonstrating, oh, they can detect the difference between a pear and an apple, do they offer like some parameters you can set and then just like use their training data to essentially do the same thing?
I believe so. I can double check, but the way that they're actually training it is just like a log, like, or like that, you know, they're training a model with just the log of the JSON of like each of the 10 sensor readings when they put a banana in the box, and then they're like labeling that as banana, and then they're just making the model such that it like makes those different like regions where like, you know, each of the different like it won't just be like in a given box, you know, they'll do in different situations or whatever. So there'll be a neighborhood of banana samples, and then it's just like, how do you create the vector space that gets these different neighborhoods, you know, spaced apart? Does that make sense?
Yeah, it makes sense.
But so in that case, they're not trying to train it to be optimized to differentiate as many different things as possible. It's like, how resilient can I make it for this one specific thing, which is just like, that's one of the two directions you can optimize. And it's really easy with like to do that with a low number of sensors, as long as like the atmospheric composition in any given house isn't going to be that different. If you're talking about more like complicated environmental sensing applications where maybe you want to deploy the same model to a forest in Africa and in the United States, that's going to be a lot more of a problem. And that's where I think you start to need like kind of baselines with much more specific sensors to kind of get like a background read that you can calibrate to. Because right now, like all of these kind of vector spaces that are like, each little neighborhood of scent is placed in are not really like grounded to any baseline reading of the, like level of whatever in the atmosphere, right? It's all like completely arbitrary parameters. Does that make sense?
Yep, totally makes sense.
I have a few different questions, and either of you might be able to answer them. Both of these talks were really fascinating, by the way. I enjoyed them. This is really cool work. I've done a little bit of work with organic chemistry, where we sort of you do spectroscopy, which is sort of a similar thing where you look at signals in higher dimensional space. But for organic chemistry, for a long time and still in the field, those signals are looked at by humans. So you have like the NMR spectroscopy or IR spectroscopy. And oh my gosh, some of the older scientists I work with are absolutely cracked at this. Like they can look at the graph and it's be like, oh, it's this. Is it, I mean, AI is very cool. I'm a AI scientist, but would it be possible at all to sort of see how good humans could get at looking at sort of some graph of scent over temperature with these kinds of sensors and just sort of say what the scent is from there?
This seems like Yo-Yo, you had the example of the woman who was really good at, like, was it she could detect stroke victims or something?
I think the old woman could detect Parkinson's disease, yeah. And aside from disease, you can also create, I think if just like if you put a sensor on the human hair or there's like a closed space of concentrated smells, you can record the individual's scent and then put it in a vector database.
It's
And then
very
you
cool.
can compare, yeah, you can do some similarity comparisons across humans.
But I have a hard time believing someone, because the chart you would have to look at would be like you'd basically have to be comparing the peaks of 10 different graphs over time and trying to infer the underlying shifts of different concentrations and have like a table in your head of like the dissipation rates of different compounds and stuff. Like it would be very difficult. I think that like the way that humans develop an intuitive scent like recognition system is just like we're just so good at processing the combination of lots of different inputs in this way. Kind of like I don't think it lends itself well to extracting this kind of feature from visualization. It's like all right, how should I say this? I mean, this is probably something Yo-Yo can speak more to, but it is a very weird sort of space that scent like takes place in. It's not like there isn't really an intuitive way to represent it in my head, other than like to the extent I can represent any bizarre, fuzzy, high-dimensional space in my head.
Wait, I was going to say not a direct answer, but similar to how humans perceive like emotions are in different parts of their body, it's actually just another hyperspace that humans uh, they needed some physical substrate to represent it. So they project it onto parts of their body.
Interesting. That's cool. I was just curious because I know sort of you showed me graphs that looked a lot like the organic chemistry spectroscopy graphs, and I was like, I wonder if humans could just sort of look at that and get cracked at it, but it seems like maybe not.
Maybe they could. Maybe they could see like the trend and the lines and stuff, but we'll see, I guess.
Yeah, that's what I'm wondering about because organic chemists are good at this because the field existed for a long time before we had the computing power to do this stuff automatically. And so, but this stuff is more recent from what I understand. So I wonder if it's just people are leaning on the machines a little bit more, which there's nothing wrong with. That's a really useful thing to do.
Well, yeah, so
I
like, a human can pick out a signal if it's easily represented in like a 1, 2, or 3-dimensional medium. But like with ML, like what machine learning is good at is picking up stuff that is very high dimensional, very nuanced.
Yeah, and I guess
So if the
perceiving
sensor
higher
can pick
dimensions
it
is
up,
your
then
area of expertise.
This
Um,
does have to like to work. You do have to have the event detection well tuned. So I feel like that's why humans are so good at like like part of it is this like high dimensional combinatorial processing, and then but being able to like associate that with specific things is its own challenge. Like that we're kind of hand waving to the training process, but like it's very easy if you're just like let me put a banana in a box, but like to extend the system to learn in the field is a lot more complicated, even for relatively identifiable sense.
so that's actually a nice segue to a couple of my other questions, if Addie will permit me.
Go for it.
Awesome. I'm curious. So we have this process. It's sort of higher dimensional. It reminds me of a lot of work I've done in like multiomics, where you're working with proteins and stuff. Obviously, or it seems like the way that the sensors detect sense isn't anything like humans. I'm curious if the way that the current ML approaches sort of detect sense on the computational side is anything like the way humans do it, or if we're just doing a completely other thing in higher dimensional space and humans are
No,
doing
I think
something
it's
else
pretty
with
similar.
cognition.
Yo-Yo
Okay.
can probably speak to this better, but I do think like it does seem like this is just more or less the same type of like combinatorial processing that human olfaction works by, or whatever, like any type of olfaction. It is just the comparison of the different cross sensitivities across a huge network of different receptors.
Yeah, and then I think you can in ML you can do some like clustering or dimensionality reduction with the initial 384 dimensions, which is also similar in the human brain.
Very cool. Very cool. Okay, that's interesting. I am also curious where if you guys, and this is a little bit of a little bit out of scope of what you presented. So if you don't know, just tell me and I'll look it up myself later. But I'm curious if you guys know where sort of synthesizing scent is at, and in particular, if there's any sort of thing where you can detect a scent and then try to synthesize a scent that's a lot like the scent you detected. Um, so if I can sort of like record a scent and then transmit that recording to you some kind of way.
That is in the like that is actually one of the first things Yo-Yo mentioned being really interested in building. I think that was in one of our earlier PowerPoints, but yes, basically. So there's a place near Yo-Yo and I are in San Francisco. There's a place nearby us that is a museum of scents that we were going to try to go bring a board out to and get some recordings of some weird, very strong scents and try to recreate them. There should be a way to like first train it on an array of like perfumes, right? And then, or not, like essential oils, whatever, things that have like kind of just like base notes. Again, like it's not really the same as like there being like with taste. There's 5 different types of affect or whatever, and it's relatively easy to combine. I have a sense that as long as you have like 30 different relatively differentiable scents to work with, you train to differentiate those, and then you get like any compound, like whatever arbitrary scent should be able to be represented as some combination of like the 30 scents that you initially train for that are like your input mixture. And then I think you can end up getting relatively close this way by just combining it in those ratios, depending like related to the way that the training process works, where it's like you're labeling the condition, you're training it, and you're measuring the response and just aligning those at the same time. Like I think for the same reason that it works like that, as long as you have enough base scents that are distinct enough, it should work relatively well.
Yeah, actually, interestingly, I started thinking about this idea from a scent room, so I was also handing out people paper strips with like combinations of top notes, base notes, and middle notes of smells, and there was only around, I think, 40 or 60 smells, if I can remember correctly. So yes, paired with micro diffusers, I think it's fairly feasible to create like at least fruity or flory smells.
That's very cool. It reminds me a little bit of the Professor Farnworth's smell telescope in Futurama. Um, very, very cool. I got one last question, and then I'll cede the floor. This is so fascinating, guys. This is really cool work. I It seems like there's all these specialized models to detect this scent or that scent. It seems like for machine learning, if you wanted to create like a generalized model that could say, this is, here's 100 cents and this is this one. It seems like for generalization, you need large amounts of training data. And I'm curious if you guys have any idea where on earth you would get that kind of training data from for sense. Because it's not like there's an internet database of sense like there are images and text and all of that all over the internet.
I think that similar to the point on can you synthesize sense, like because of the way scent works, and there are like hundreds of different actual like specific sensitivities that are all kind of combined, like, but you still can reduce that to a lower dimension, right? Like you still can be like what a perfumist does intuitively. There are, and actually this is to your point earlier, and this will kind of synthesize things well. There are people that have a talent where you show them like any given perfume and they're like, cool, I know how to make this out of the combination of 15 different things. That is like, even though the native, like, like chemical sensitivities that scent is composed out of might be totally different in the things that they're like, how should I say? There's 500 different sensitivities in both cases, and each one is a bag of like 40, and there's no real overlap in the materials to make the one perfume and the other. They can still align really strongly if you like it for a good perfumist, right? Like they just have a model in their brain where they're like, I can make whatever out of a relatively known number of inputs, right? That's kind of what you end up doing with like the like compression later, where you end up being able to get like that whatever 3D plot that you can put like banana, orange, pear on. So like when we're trying to do like the perfume synthesis, when we do the training to first be able to distinctly identify those 30 things, we're already creating the system to be able to represent complex mixtures of scents that are not made out of like, those dimensions natively out of those dimensions, if that makes sense. So like something can smell like vague, like one of 30 vague ways, and as long like if you can represent something in that space, because of the fact that there's the underlying like mix of grab bag cross sensitivities, like that's fine. Does this make sense? So similarly, like
Yeah.
You should just be able to, like, if you can find a way to align these arbitrary dimensional spaces to like baseline references of specific, like, it doesn't have to be all of them, right? But if there are some specific like basic compounds that are like the lowest level, like, thing that you're actually detecting, and you can just like calibrate to maybe 5 of the actual baseline level of those in the environment, then you can start to align these arbitrary vector spaces and start to actually like have a more global data set. That is like an additional process on top of this existing thing. So it makes like right now sensors are not made to do that. They're not made to be like generalizable in this way, and they're not calibrated to some like reference baseline of a given specific chemical, which is kind of like, I think, something you would need for this. But that's kind of why we want to start playing with the addition of very specific nice sensors for specific compounds.
Very cool. Okay, awesome. I will cede the floor. I have many more questions I could ask. This is really fascinating. You guys are doing awesome research. Thank you for presenting.
Thank you.
Thank you for your questions. Yes, Tigran, you can go ahead.
So I came late, that's why the first question is going to be technical. Do you guys have a recording or something similar that I can check later on to like understand better what you're doing? And then I'll ask you.
Yeah,
like,
I'll have a recording up on my channel, and we'll be posting it on X as well, both of us.
Cool, okay.
I can also share the text.
That's cool. So yeah, Yo-Yo is my friend, so I can learn through her, but I've been meaning to make it on time. Anyway, so the questions itself. So two areas that might get you guys funded or might just be curious about your work is probably like, so the least far-fetched is like perfume itself, right? Like big perfume. I don't know how does it operate, but like I could imagine that even in early stages, there is some crazy guy in perfume industries that really wants to give you money to make sure that he has a competitive edge over his like alternatives, competitors. Then the other thing that comes to mind is like XR as like a large umbrella, because XR is actually not just VR and AR, right? XR is like everything. XR is like sound, the vision, all the senses, and optionally even like additional senses that we don't have now. And so just curious, like, does it make sense for you guys to talk to like these industries at this stage? And if so, who did you talk to so far?
I think XR makes a lot of sense. Um, was thinking about using smells for video game designs, and this could be joined with some like hackathons, indie game design festivals, and so on. Kind of like sponsor technology. It will make sense.
For those joining late, by the way, this is the board itself, just for a sense of the scale of a relatively minimal implementation. And this pulls like maybe 300 milliwatts. So this is the solar panel to run two of them. So I do think it lends itself well to like wearable stuff and environmental surveying for this reason. But
Yeah, I'm excited about the environmental surveying aspect of it. Another question I have is, are there sensors that can be used underwater for like river or lake or ocean ecology?
I think
probably
there would be,
probably
yeah,
they would be different
because the
types.
pressure of the fluid would change, and that is still detectable.
What you're saying,
I
though,
think it would. Oh, sorry. Go ahead.
are you saying yes, it is effective in water or not?
Like
This specific implementation, no, but there are some that would work on the same principle, more or less.
yeah.
Really cool. So, yeah, I mean, biological research. I mean, because anytime you have chemical sense, you want to parse out like a scent marker with like a biological event, something like this. I mean, you can. There's so much to research. Also, yeah, medical stuff. I mean, Parkinson's is one thing. I mean, aren't there like dogs that can sniff out cancer somehow, or something like that?
Yeah.
Or anytime you have a dog sniffing for something, is it possible to have a mechanism that does the same thing? I mean, this is like go to airports.
For sure. That was actually one of the first evil commercial implementations I thought of, was like, I'm sure there's a way to, police public spaces to keep people from smoking. I don't know if that's evil. It's probably a net public good, but and then definitely like for the like allergen detection, that is like something that there is existing work on, and is a viable implementation for sure that you can just find an example that will just work for. And even if you don't know exactly what the allergen is, Daniel, like as long as you're like the sensor is continuously logging and you can like differentiate the event like in time more or less, and like you should be able to train it.
Yeah.
But and that starts to get into the more interesting multimodal applications also, where it's like
Multimodal is cool. Yeah, you can also lower the friction just from thought to action by also having brain-computer interfaces. There are BCI companies like G-Tech doing horse research, horse BCIs. So if they can also smell things and then have EEG directly translated to meaning and concepts with the help of language models, that would be so much cooler.
Wanted to add that Daniel's question in the chat seems like a real market. Like I looked it up with ChatGPT and it's like a niche market that's not commoditized yet. So I don't know how easy is it to implement something like that, but it's not just Daniel's wife. Like there are a bunch of people with that or symptoms like this.
Yeah, it completely ruins her day every time it happens. We know what the scent is now. She's figured it out. She's been dealing with it for a long time, but it's just like awful migraine. She's out of commission for the next few hours. So that could be a really cool market. And I think we would pay some significant amount of money for a little detector that she can wear on her that can just tell her she needs to head out of whatever area she's in before she gets a migraine.
And a similar thing, I don't know how relevant it is that something like this happens with eczema, psoriasis as well. Like this like small undetectable things in the environment basically cause really bad allergic flare-ups. And sometimes it's like dust mites and stuff like that. So I don't know if they're detectable through smell in any way, but I just thought it's like an adjacent problem. Otherwise, I don't know how relevant it is.
Well, cool. Also Alzheimer's is detectable. And I guess this has been already used in ancient history.
How was how was it used? Like I actually don't know what you're referring to.
I think vaguely in some cultures and mythologies, there are people sniffing patients to diagnose conditions.
Oh, I have a whole thing. I want to talk about this later. Sorry.
Go ahead.
No. I want to let everybody else finish with their questions because once I start, I won't stop. That's why I'm waiting till.
Applications in food. You mentioned bananas, I guess, but like, oh, if you wanted to perfect, beer brewing or something like this, I'm sure they already have yeast detectors or whatever they're looking for, but better
Oh yeah, for sure.
chemical sensing for all kinds of stuff. Greenhouses,
Yes,
for
perfecting food. And also a few years ago, I was working on the system that detected when meat rotted ahead of time by detecting amines, and then it converted it to like a changing color strip that was on the food packaging.
you can make microwaves even more complicated with their whatever.
This is probably not a profitable application because unfortunately solving substance use issues isn't profitable, but I'm involved in substance use research. And they have places where you can go and safely ingest whatever the substance is so you're not in some really sketchy place. And there's a large issue with sort of different things being laced into substances being distributed on the street, like fentanyl being put in everything, even stuff that's not supposed to have fentanyl, and xylazine, and medetomidine, and all of the other things. And a lot of people say that if you once you know, you can smell whether or not those substances are in something. So I think, and these locations where you can safely ingest drugs, just a little detector on the wall that lights up where it says, "Hey, just so you know, this has medetomidine or fentanyl in it," could be a really cool application and warns the person ahead of.
Yeah, that's right. And detecting overdoses ahead of time.
Addie, unleash yourself.
Oh man. All right. So first of all, this was. I'm so happy we got this set up. I'm so happy because it's clear that everyone else likes it and I do as well. So a couple of things, right? So the first thing is, we've talked a bit about this and this olfactory language project of mine that I've had for quite a while. And the thought experiment that sort of jump started that. I mean, it was a couple other things as well, but one of the main ones was that I would think about the ways that we interface with our world around us, right? The way that we kind of make sense of the world using our sense, pun intended, right? I saw Dugan made a joke about that earlier. But so I would think about like a dog, and I think about how does a dog even know what's happening in the world, right? I mean, and then there's an aspect of myself where I'm like, if their sort of primary interaction with the world is say through taste or olfaction or smell or whatever, right? It's like, I wonder if that's also the way they would model things inside of their minds. Because a lot of us, even if we have aphantasia, like we still model things in terms of the sort of idea of numbers or shapes or words or whatever. And I'm saying phenomenologically, the way that the quality that they're actually experiencing when they're thinking could be smells, could be olfaction. So the initial goal with this, a large part was that can you think in smells by training on an olfactory language? And in order to do this, it's actually relatively simple. If as long as you have something that smells like a perfume or a cologne, you can basically kind of try it on your own. But the first thing that I kind of started with is I said, okay, let me take like pieces of paper, take those pieces of paper and then put like, take the colognes or whatever, put them in a dropper bottle and then like make little patterns with them. So they'd be like letters, but they weren't literally letters. They're more like symbols, right? And so I'd make them in these different patterns. And through each time I'd smell that and focus really hard on getting, a sense that at that scale, like the direction of the smell or the different texture or whatever of the smell. I would associate each sort of smell letter with another smell letter or some other thing in my head, whether it was an idea or like a memory or whatever, right? And you're basically just building associations with smells to the point where you get really good at directly interfacing with the smell and not through the other thing. So one of the things that I would try is I would associate some kind of number or something with the smell, and I would try to smell math throughout that. Because I was learning it as a kind of language, as a way of transforming it. So what ends up happening is if you really try on this, and for you it could happen in a day or two, or maybe a week if you try enough. But what'll start to happen is you'll kind of get this afterglow where there's a kind of transfer effect, and you can take, so you know how you can use English in these words right now to describe your sense of self or different quality or whatever, right? Well, you can also do that using the quality of smell, and you're not thinking in words anymore. You're thinking in smells. It's very, very strange. I think if you've had certain dreaming experiences or intensive psychedelic experiences, you could probably relate to this more for those that have gone through those types of things. But it's a very, very strange thing. And one of the sort of ideas that I wanted to test with this as well, because in the beginning I said there was also some other things, is that I thought that language and synesthesia were basically kind of the same because they're just associations with each other, right? Like when I look at, letters on a paper, that's a visual representation of something else, right? So when when I'm reading, a Wikipedia thing or something, and I'm, doing it in my head, there's a voice and there's another thing that's being associated with that, right? So I'm like, just by looking at visuals, I could get a sense of audio or hearing or whatever, right? And even then, like those, you could train somebody using the same letters of English or whatever, and it could mean completely different things. And in fact, we already do that when we have, in lyrics, we have things with double meanings, double entendres, all that type of stuff, right? So this isn't anything new, but I think the thing that was very cool is that you could literally feel and think in terms of smells. And so what I'd be wondering on the sort of philosophy side of this for just a moment is that if a computer is using sense and olfaction to compute, what experience is the computer having internally when it's doing that? Again, this is more of a philosophy consciousness thing, but entertain me if you will.
Yeah, I like that. I mean, spoken words are just the synesthesia between concepts and audible signals.
Right.
So you can loosen that up and associate concepts with other sensory data, other words, but not audible words, just different qualia.
Yes, and also the use of different kinds of memory of different lengths, as well as attention to focus on the different smells, or for the computer could be interesting.
Yeah, because I think about, we there are a lot of people that are kind of talking about how we can bring aspects of a computer into our own, bodies or minds or whatever. I guess that's sort of the transhumanist crowd. And it would be interesting to sort of understand the sort of deeper way that computers would interface with things like smell versus how a human or a dog would, right? And it would be interesting to just see, because I think the thing that got a lot of attention on my end from what I was thinking about was like I was wondering, let's put it this way. Let's say you're trying to make a painting, right? So this kind of goes into language and representation, right? So I want to make a painting. I want to make a painting or a drawing of Yo-Yo. We'll even just say it's in black and white, all right? If I just think directly kind of one-to-one, in my mind visually and in the format that I want to express it and represent it in, then that's a relatively easy thing to do, right? Compare it to thinking more abstractly and creating some distance between those kinds of points of perception, right? So something that I've talked about before is that sometimes when I'll be thinking of, a sort of beat that I want to make or a drawing, as I'll think in smells or sounds and then convert that over to visuals. And the thing that's weird about that is that you can do a lot more dramatic changes if you work at that abstraction level by going far away from the thing that you want to express it in, and then you convert it back. Right? It's sort of like I also give an example about like you have a Lego set or something. If you want to have the same groups of pieces, but you want to use it in different ways, you have to temporarily remove the pieces and give it those degrees of freedom to be switched around. And so I sort of think of senses and perception like that. And the point that I'm getting at is just how we say, we think in terms of words or numbers or whatever. Do you think at least in your own way that you've looked at this, are there benefits to thinking in terms of smell, whether that's a computer for those designated tasks or for humans? Like, what would be a benefit of thinking in smells instead of thinking visually, maybe?
I just want to add something before the answer. Like the Nick Camerata was asking about this recently. I was like, he did a big poll. Is like, what percentage of your net worth would you be ready to pay to have a second, to have like the smell of a wolf, which basically will be compatible to like the vision of humans. And like, I think the numbers are pretty high. A bunch of people just want to go cyborg with olfactory senses. So
If you're thinking in terms of smell in the internal monologue, then usually it gains a higher frequency, just like how what words do to people, and perhaps you can just like easily interface with the environment, such as there are in I guess indigenous people doing things that are involved that are like more grounded with the environment, and then maybe you can smell certain animals or changes in weather patterns, etc.
Yeah, and I want to go to a point you mentioned earlier about cultures and the way they would look at smell and use smell. So yeah, like at points in medicine and human history, smell was used. Now, animals can also sort of definitely seems like they use smell to know when something is good or bad. I mean, in a way, we already do that with foods. Like if something is really spoiled or rotten, you're gonna get an idea through smell, right? And that's because sometimes things may not appear in one other way of perceiving, but they will in another sense, right? So something may not appear visually, but you'll get an idea of what's going on through your smell. Now, also the other thing is that like dentists, like really good dentists will kind of have an idea of what's happening in your mouth with your gums and your teeth and everything and your oral health by the smell. And I talked to one at one point. He's like, there's it's very similar to like what people who make perfumes do. Like you get this very subtle distinction between the smells and where they are. And he sometimes he'd be like, yeah, I'd sort of think about like if I took one smell and another smell and combine it, what would that look like? So one of my interesting things that I was thinking about was, if you take, on the topic of some smells being indicative of a disease, is that if you're able to think of the smell, internally in your mind as a kind of language, could you then combine different smells that would be like a prediction about what another disease would sort of look like, right? So, we do this a lot with visual representations of things all the time. That's pretty common for humans. And I think it would be very interesting if by interfacing with the smell or the analog of the smell of a disease, right? Which is what we do with data if we can't get the direct thing anyways, is, could you predict what another disease would smell like if you could think in smells? And I think thinking in smells applies to humans, definitely applies to what you're doing with computers as well. I'm just wondering if you've thought of that.
Not yet about diseases too much, but it would be interesting to like decompose each disease and recombine them.
Well, I had more engineering aspect, kind of like if I just got this uh got like a random breakout board from say SparkFun on this BME sensor, do I essentially have to use the Bosch stack in order to extract all the vectors out from it, or like is there a quick start someone has already like done for this? I kind of looked at Lucy's repo, but it looked like most of the stuff was for that board that he created, right? Just curious if there's like something I can just like, I don't know, just start extracting the vectors and then messing around with it kind of a thing.
Oh yes, for the Bosch sensor, Lucy and I were playing initially with AI Studio, which is their software, and they have a simple example of like distinguishing if you record 30 minutes of data from a coffee jar or a jar without coffee, you can distinguish the both. But my question to that is it overfitting and how generalizable it is? Is it? Yeah.
Yeah, yes. I guess like for the hobbyists, for me, like I just want to detect, did the dog poop or not, right? Like the path to completion there. Like, I mean, the ESP32 is a moderately decent processor, but would it be able to like say, you know, do the appropriate like mapping all in memory right there to determine that? Or would I assume I would probably need like like a computer somewhere, right, to actually do the processing, right?
The training is, can
I
you all
think
hear me, by the way?
I mean,
sorry, Lucas, go ahead.
once I train it, right, and I get some randomized vector, right, maybe I do PCA on it to find roughly, oh, this goes to like, reduce the dimensionality to like 10 or something like that. Like simply, the hot dog or not hot dog kind of a thing. Like, I assume I can't do that on ESP32, right?
Well, so the training process is actually done through the like Bosch AI Studio. That will make it like really if you
No,
order
no, I
multiple.
get that part. I'm just asking on the inference part.
Oh yes, no, totally on ESP32 because the hard part is that algorithm that mixes the output of the different sensors and the heater profiles. Like training those, once you train those correctly, it is very sensitive, like or sorry, very selective. Um, so there's like an edge model inside of the actual sensor itself. Is kind of one of the selling points of the BME688 is that once you have the profile well configured and like tuned via AI Studio, the selectivity is kind of baked into the heater and signal mixing profile such that the very low power processor is able to reliably detect the one specific event. So that's where it gets really exciting actually, because if like this is why it's such a useful thing for like fire detection.
Okay, yeah, thanks. That's kind of basically my question. So basically, like that board you created, you could kind of like upload the
Mhm.
edge model or whatever, and then just like throw it somewhere in the field, kind of a thing.
And if you have 8 of the actual BME688 units versus just one, the chances that you take a pre-trained model and you just throw it on a new board and it just works and reliably detects versus you have one sensor, way higher. Because the variation kind of averages out, if that makes sense.
Wait, are you saying your board has 8 of them on there, or?
It has 8 in each individual little unit. So like each individual one of these has 8. But if you have 8 of these for 64 total gates, then I'm saying you get even better like resilience to different environmental conditions.
So your board actually has like 8 or 64 of those on each one. Is
This
that what
one
you're saying?
has a single sensor with 8. I
Oh,
have
okay.
another one designed that has 8 sensors, 64 total, same footprint. And it's just slightly more expensive. But I'll actually release that one later today. I wanted to make sure that I tested this and it all worked first.
Uh-huh.
The board, if you just order it, it's like $25 assembled. And then the way that I've set it up, you just like, if you want to add an arbitrary number of sensors, you import a submodule called nose, and you're just like, no, like nose one equals new nose, nose.i2c squiggle uc.i2c nose.power squiggle uc.power, and that's like times 8 or whatever, and that will add an arbitrary number of additional sensors. Which you should like if you just look at the Adapile documentation, it tells you basically how to set up the PCB and reconfigure it as a Python package, which I won't talk too much about here. But so basically, if you're curious if it will work for a specific application, $30 and try it, and probably it'll take you like 4 hours start to finish tops to get something tuned, and that's probably like way too high of an estimate. That's assuming pretty minimal background with embedded.
Do other people have more questions?
Yeah, I guess I have a couple other things. So, what do you think this project of yours will look like, say, a year from now? I mean, I don't know if you've thought of that, but just in the case that you have, like, what if things kind of go well into plan? What would this sort of look like in a year? Because I think this is pretty interesting.
Yeah, we were thinking about 2 branches of it. On one hand, we are doing more artsy installations and cognitive science discussions around the project. We can do this at museums or festivals. For example, Lucy mentioned open source. And on the other hand, we can have like if people want to build with smells themselves, we can create a dev kit that just is similar to like the conceptually similar to Oming AI, and people can contribute to it.
I like the dev
We
kit
can add
idea.
on.
That's a really cool idea, I agree. I was gonna ask a similar question as in how can we help you guys? Like, what are the possible ways for an outsider to contribute, or alternatively, if you're open to people joining your team, who would be the ideal candidates?
Extending to other microcontrollers and testing with other sensor platforms, and really long-term moving away from relying on Bosch AI Studio and being able to design our own training platform would be like an amazing goal.
I mean, the primary
think
purpose
for
of the
now-
Bosch Studio, right, is to execute the I2C commands to get like the vectors out.
No, it's to take all of those, like the JSON files with all of the different sensor samples over time and train like the actual edge model from those. So it's the training process and everything like that as well. And then like we'll derive the heater profiles and stuff.
For now, for people interested in this project, they can join our Discord server.
Do we have a
Yeah,
Discord server now?
definitely send that.
I just created one right now.
So true.
A classic example
Yeah,
of
we'll join that. My other question. So I think you've seen that people are really interested on the Salon today. So I would like to set up a follow-up at some point. When would be a good time for that?
I'm very flexible. What about in 2 weeks? Lucy, what do you think? What are people's timelines looking?
I think maybe slightly longer to give us some time to cook.
That also makes sense.
Yeah, y'all gotta be locked in cooking.
Mm-hmm.
Yeah, I
Yeah,
think
we could do
if you want to
2 weeks to a month or so.
Yes, 2 weeks to a month. If it's slightly shorter, then I guess the conversation will be more theoretical and long term will, like if it's slightly longer, then there will be more tangible demonstrations.
Because the thing that, as we've sort of spoken before, I'm very interested in like biohacking and cognitive biohacking, right? Because of those cognitive hackathon things. Like that's sort of up my alley. And right now I'm thinking about how this would sort of mesh with some of the olfactory stuff for qualia and all of that. I would be interested in some kind of BCI that helps humans talk with and interact with computers through olfaction. That could also be interesting. And I guess the key then to what Dan was saying earlier about, synthesizing the smells as well, which is a whole nother thing to get into maybe for another time. But I think, why do you think there's been sort of a bit more interest in olfaction? Because I don't know if you may have seen this, but the C Stripe had made a post about olfaction the other day, and I linked or I mentioned you, and then I also mentioned my olfactory thing. So I'm wondering, like, there does seem to be a cluster of people that are pretty into this, and I'm wondering where did that kind of start from, and what does that look like in the future? Do you think, since you're on the sort of more of the engineering side?
I think that it's easier more recently to be able to like work with data sets that are not so easily localized, or I guess like to work with a phenomenon that aren't so easily localizable. So being able to do like the existence of machine learning algorithms that can do training on these kinds of like highly complex combinatorial inputs is kind of what I think has enabled people to think about weird sensing modes. I saw someone mention Varela earlier. I'm a big activism enjoyer, and I've been happy to see an activism kind of come up more recently. And I think that this is related in a certain way. Like scent kind of requires much, like it's not as immediately useful unless you already have systems that are capable like that can do more multimodal types of work. And like we're just starting to see the existence of tools like Goose that are able to combine different kinds of like memory systems and tool chains to have a lot more kind of like interesting, almost like embodied sorts of relationships with data. And I feel like this is probably related, if that makes sense.
Yeah, and also from the industry side, there are recent startups, I think in the last 3 years. For example, Osmo is building an odor map, and then they're invested in by Lux Capital. So that may have generated some of the community interest.
Yeah, y'all should you should apply for the augmentation lab residency, by the way. Did you guys see that?
I already applied.
Oh yeah.
Perfect. But
Nice.
it's they're great. They're really awesome. And I think y'all should totally apply for this. Yeah, this is cool.
Yes, I'm a
Um
fan of the community.
yeah. The other thing is like you mentioned that okay, there's sort of two branches of this, but I'm wondering what else this would be interested for. It's in the realm of of olfaction. And that's maybe a topic we can save for the next one. More experimentation, experimental applications of this whole thing. But like, give me your wildest idea of what you'd want to do with this. Just say everything kind of goes to plan. Like, what is the wildest idea of what you'd want to do with this? Even if it seems like crazy, esoteric, whatever, like what would it be from Yo-Yo and Lucy?
Oh, from my point of view, it will be like a symbiotic ecosystem, with like all kinds of, for example, I previously built with swarm robots, and then you can use haptic gestures, haptic hands to control with them. And then aside from that, like sense may also control robots and things in the environment. I want to build like symbiotic uh generation with machines, and then also just transmuting into other sensory modalities, into visuals, into sound, music, into sense, and it will be all interconnected together.
Yeah, I'm gonna allow myself to get a little bit more like out there now, since I feel like I was relatively refrained earlier. But when I like my long-term interest in kind of snake biology and cognitive abilities, like snakes have been done so dirty by cognitive science. Historically, it's like the whole tiered model of cognition where reptiles are like less aware. I mean, it's less and less viable over time. And one of the interesting things about snake cognition is that how like they will consciously limit the rate of sensory input depending on things like how cold they are, when the last time they ate was, how stressed they are. So like you can almost imagine them like turning down the rate of cognitive processing and taking in less information when they get stressed, and they're focusing really tight on really specific stimuli when they get real stressed. And like one of the indicators of this is like you can tell how stressed a snake is by how often it flicks its tongue, because that's such like a rich sensing mode to them when they're stressed or when they're really just kind of trying to focus on being physically safe. They're not really using their smell so much. They're just locked in on whatever thing is moving and big around them and kind of staring at it intensely. But when they relax, they're able to take in so much rich contextual information. And I guess like in general, I'd be really interested in can you compute across like a wide area the move, like I'm interested in like signal ecology. Is there a way to infer interesting things about complex ecosystems and like webs of relationships through monitoring the movement of sense through environment and other information, right? Like there's all kinds of interesting examples where different context, like a rainforest versus a desert, different, more or less similar builds of animals will have very different behaviors in different contexts, whatever. Is there a way that you can kind of modulate, like, or you can do an interesting environmental sensing where you like monitor how animal behavior changes if there's like, a decaying thing nearby or something, or things like that. But so I'm starting to get into much more like weird fuzzy event spaces and
Oh no,
environmental
this
modeling.
is where the fun is. I don't know if you've seen some of the other episodes of the Polymath Salon stuff, but this what you're going on about now is like half of the stuff we talk about. So this is great.
Okay, yeah, so that's what I'm interested in longer term. I want to be less like the tyranny of direct signification or whatever. Right? I want fuzzy domains.
Yeah. This is very interesting. And the other thing I was going to add to that, right, about sort of the point I was getting at is that even if we both say humans and dogs or whatever, snakes, we have a sense of olfaction and the way that we're taking it in. Okay, we're taking in smell, but I think the way that say snakes or dogs would experience the meaning of that is different. Even if we're taking the same smells, even at the same intensities, it's also sort of their experience of meaning and the way they're abstracting that, right? It's sort of like how even in humans, like we could look at the same thing and get two different meanings from it and process them in different ways depending on our backgrounds, the way our brains work, all sorts of different things. So that's also something I'm very interested in because at some point, I would like to be able to make new forms of senses. Like I've talked about this a bit, like about like, by combining senses in a certain way, could you get a brand new sense? And I also think that you probably do have something similar to that happen in altered states. And when I say altered states, I don't even mean like you're on some substance. I mean, even if you're just like extremely stressed or in sort of a life and death situation, like people will say when they're in situations like that, that their senses sort of change, their eyesight changes, their sense of smell might change, their hearing will change. There's these things that'll happen. And I think it was Dugan, we were talking on the other salon about things like magnetoreception, right? And so that maybe it's sort of there late, right, in our brains, which it seems like it potentially could be. And you just have to have the right sort of ecosystem environment stimulus to kind of bring that out. And then we can focus on training that and growing it. But yeah, this is totally the stuff that I think about a lot. I mean, this is so cool. And we need to have a conversation offline about this as well, or maybe just one where we just kind of go deep diving into all the more experimental stuff. But this is really great, everyone. This is really good. I'm happy.
For sure, we can have hours of discussions offline.
Yeah. Yeah, so the last couple of things before we head off. So go ahead and tell everyone where they can find you online and follow up with what you're building.
Okay, we'll
You can
send the
follow
links
me
in
on
the chat.
GitHub and Twitter and
Yes,
website.
I'm mostly using Twitter, and I have a personal website at yoyo.cat, as well as the Discord server previously mentioned.
Yeah, let me know if there's anybody you ever want to connect with or anything that's kind of interesting. So what we can also try for another salon is we can invite everyone over from this one, but also bring over, I don't know if anybody anybody at QRI, any good connects there, because we could totally loop some of them into there, because I know some of them are interested also in like olfaction and all that. And it would be interesting to sort of bridge Quality Research Institute, QRI.org. Yeah, it would be kind of fun to sort of have their perspective, my olfactory language perspective, and then your perspectives on this whole thing, because I think there's like a lot to explore here. Like I think this isn't even the tip of the iceberg, as far as I can tell. All right, thanks everyone for joining this episode of Polymath Salon with Lucy and Yo-Yo on Scent Computing. This was super cool. We're going to have them on again to present more in detail and sort of more of their ideas and ways they want to take this. But in the meantime, this Saturday, May 17th, we are doing an in-person Polymath Salon with Scott Aronson, who's also a UT professor, very, very brilliant thinker. He is going to be here with us at UT Austin for a Polymath Salon on computational complexity, theory of mind, physics and math, quantum computing, unconventional computing, metaphysics, all sorts of really, really cool things. And so, yeah, that's going to be at UT Austin from 5:30 to 9 Central Time this Saturday. I may have another small pop-up salon somewhere else in Austin on Friday, potentially. I'll keep everyone posted. Yeah, that's what's on the horizon for now. I'll have the links for everything in the description. And yeah, thank you again, Lucy and Yo-Yo, for a very great discussion today.
Thank you so much for the fascinating questions as well.
Of course.